Okay, we're recording now, and I'll go big screen. Okay, so the very first topic on paper 1 is data. Okay, data representation. Okay, I'm going to make this a little bit smaller. Data. Okay, that's the very first thing. Now, what you have to be able to do with data is go from binary, or I guess, it's going to be denary. We start in the human language, denary or decimal to binary to hex. Okay? So you need to be able to convert from one to the other. You need to be able to go from here to here, here to here, and here to here. And plus, there's one more that you have to be able to convert, plus BCD. Plus BCD. So I'm just going to quickly outline, if you have your summary note, let's just put a nice picture about all these ideas. So what is denary there, Wendy? Tell me what numbers are denary, who uses it?
From 0 to 9.
Yes, denary is the human. It's base 10, okay? This is base 10. Binary is base 2, and hex is base 16. In decimal, it's 0 to 9. The numbers are 0 to 9. Binary can only be a 1 or a 0. And hexadecimal is 0 to 9, and then it goes A, B, C, D, E, F. I like to write this out because sometimes I forget which letter is which number. And so on your exam, this is something that you have to memorize, okay? You're not going to be told what is A, B, C, D, but I just like to write it out, okay, 10, 11, 12, 13, and then I know which each of those letters. Okay, it's really pretty much easy to think about the F. It's 15, but sometimes like a D, you may want to write that out. And now, the question is, how do I go from decimal to binary? Okay? If I'm going from decimal to binary, let me see if I can't run right up there, but what I can do is I can lasso this, and then I can move this. Oh, going to lasso this, and then I can move this down. Can I? Why isn't it moving down? Doesn't like me. Anyways, I'll just write down here. So, when we go from decimal to binary, basically there's two methods. You need to show your work. And you can either use a table or the division method. The table method is 2 to the exponent n, where each of these are called bits, right? And this is going to be 2 to the power 0, 2 to the power 1. So this is going to be 1, 2, 4, 8, 16. And then you're going to start on the leftmost bit, and then you're going to put in your ones and stuff like this. Chad, what is this binary number in decimal or denary? What is that?
5.
It's equal to 5. And so just remember that you want to use a table. Wendy, what is the other way that you can go from decimal to binary? So we can either use a table, or what you can do is you can divide by 2. And if we have a remainder, it's equal to 1. If no remainder, it's equal to 0. And then you can put 1 zeros, 1 zeros. But it's up to you what method you want to do. Okay, Uma, after we have base 2, how do we go to hexadecimal? How do I go from...
Just split it into 4.
Yes.
And then you add them up, and it will be 1 to 15, and then 0 to 9 is 0 to 9, and then the rest is 8.
Correct. So what we do is we, from the least significant bit or the right most significant, the right bit, we group in groups of 4. Okay. So when we're going here, what you do is you put groups of 4 bits. 1, 2, 3, 4. You convert this to denary, or and then you just double check it goes into like the hex, because if you have 13 or 14, you have to use a letter. Okay. So let's do this together. Chad, what is this equal to?
5.
This is equal to 5, and then this is equal to what? If we have 1, 0 here, so what is this going to be?
0.
It's going to be 0. And so it's going to be 0, 5. And this is the hex number. Okay? So you need to be able to go from base 10, base 2, base 16, and then vice versa. To go the other way, to go this way, from hex to binary, what you do is you take the hex number and you split it up into 4 bits, and then you put the table 1, 2, 4, 8. This is going to be the maximum of the table, and then you just put in the bits that represent that. And that's the reverse process. From this there, Wendy, how do I go from the table to denary? How do I go from the table to denary?
It's like you put all the 1 or zeros in the table. If there's a 1 in the
Yeah,
so that you just add the number.
that's right. Basically, if you have a 1, you just add them together. So this is just going to be 4 plus 1 is equal to 5. Okay? No problem there. Let's go into the A-level concept, because this is all from grade 9, computer science. What is BCD? BCD stands for what? Yeah. And what this is used for is for digital clocks, where we have different digits, and BCD is used for clocks. You need to know the application of these things. So I'm just actually going to scroll down. We know that there's 3 data systems that you need to understand, and then you need to know how they're applied. So I'm going to talk about color, the RGB colors. I'm going to be talking about clocks, and some other applications. Also, MAC addresses are in there as well. So let's talk about the data conversion. We're okay. Let's talk about the application. Now, the application is how we can use these things. Some applications we have are BCD, we have MAC address, we have the RGB colors. Okay, let's talk about BCD. BCD is used for clocks. And basically, if I have the time is 9:05. What BCD does is for each digit, we make it into a byte of data. And if you can actually put 2 digits into a single byte, okay, as well. So what this does is we take one digit, and we make it into 8 bits. If we want to compact it, we can actually put it into 4 bits. Technically, the numbers of a digital clock can only be numbers 0 to 9. Agree or disagree? Okay? And so we can actually save this data into 4 bits. 1, 2, 3, 4. Because it's 1, 2, 4, 8. And so 4 bits is enough to represent 1 digit. Because we're not going to go over 9, right? Because then it goes into the next digit. But this could also do the army time too. But actually no, because each digit can only go up to 9, even in the army time. So right here, number 5 will just be like this. And so I can codify a digit into 4 bits. And then I could put a 0 here. I have 4 more bits, so it's going to be 0, 0, 0. And so this is representative of the 0, and this is the representative of the 5th one. And that's BCD. BCD is a way to represent digits into binary. And it's a way to shrink the data down. We have 8 bits BCD, and we have 4-bit BCD. 4-bit BCD means we can put 2 digits in 1 byte. Okay, there's 2 types. Cool? MAC address. Who can tell me about MAC address? Yes, Uma?
It consists of 12 hex specifications.
Yeah, it has 12 hex numbers. And it's in your network card. And so it looks like something like this. You know, 0, F, A, and it has these little thingamajigs. You know.
12 hex decimal, which is equivalent to 48 digits.
You get this long hex thing, and it's used for identifying the hardware of your device. It's used to identify the hardware, and it can't change. Can't change. And it shows you your hardware. And so I can use it to figure out what kind of computers on the internet. Each device has a unique MAC address from the manufacturer. Cool, that's an application. RGB, what is RGB?
There's 6 hex decimal.
RGB is to do with colors where we have.
It's usually a hexadecimal color code with
Yep.
6 digits. 6 hexadecimal.
Red, green, blue. And with these colors, you can have FF, 0, 0, 0, 0. What this represents is the maximum you can have is FF, 2 hex numbers to represent 1 color, or 256. 255. And so if I have FF 0000, it just means that the color is red. Agree or disagree, right? And if I want blue, I can have 0000FF, or I can put 2 colors together. Let's say I put red and green. Red and green makes what? Orange? I'm not too sure. I'm not in art. Maybe Wendy knows. What happens if I have FF, FF? What color will this be?
I think it's yellow.
It's going to be yellow. This is equal to, what is it? This is equal to red. Okay, so you need to know the applications of number systems. Okay, that is part in the data representation. Okay, so we did BCD. We were able to calculate. Okay, and then, oh, there's one more I forgot. It's called ASCII. ASCII is an important application. What is ASCII / Unicode? Who can tell me what is ASCII and Unicode? This is the application of number systems. Yeah. Ched, what is ASCII? This is on the call sheet. Can you look at your paper 1 test, the practice 1? What is ASCII?
Has 8 bits. Can we do it in English?
This is an 8-bit code for the keyboard. Okay, it's called American Standard Code of Information Interchange. Okay, so the very first computers, in the 1980s were mostly developed by IBM. IBM is an American company, and they developed the standard keyboard that we have today. Each letter is represented by a binary number, and it can also be a hex number as well. Okay, there is an ASCII table that you can look up. But there's, and it also has 8 bits can also have some symbols. Yes, but it uses actually 8 bits.
Yeah, because the 8 one is 0 all the time. And then the 6.
There is actually 8-bit ASCII. It can be 7 and 8-bit. There's different types because sometimes you have different symbols. So you can use the 8-bit as well.
The 6-bit changes from 1 to 0 when it's uppercase.
Correct. The 6-bit is the difference between a capital and a smaller case letter. Okay, so that is reserved for upper and lower case, and then it goes sequential like A, B, C, D, E, F, G, capital, lowercase. Okay, have a look at the ASCII table. Wendy, what is Unicode?
It's like the generally used
There's a problem with ASCII, and we need to fix this problem. So what does Unicode do?
The Unicode can deal with the code that the ASCII cannot do, like the Chinese words.
Yes.
Or the
We have other languages.
And ASCII only uses.
It uses, I believe, 16-bit. You can also have a 32-bit. There's different versions of Unicode that you can download. Depends on how much language you have. So, for example, Chinese, is Chinese included in ASCII? Check. Can 7 bits represent all the Chinese characters? There's 10,000 Chinese characters, right? And so to figure out how many bits, it would be 2 to the exponent 7 would tell you how many different combinations you can have. Is that 128? 128, something like that? So that 128 can do the English alphabet. It can do uppercase, lowercase, and symbols. But it cannot do Chinese. And so when you have Chinese on your computer, it's using Unicode. So write this down. Unicode uses other languages like Chinese. Okay? Because Chinese has like 10,000 characters or something like that. Right? That's not going to fit in ASCII. ASCII will most definitely be on the tens. Okay. So this is, again, applications of number systems. Let's go over here. The next thing is graphics. Okay? Again, this is review. We have covered this before. It's been a long time, but it's going back because that's how we review is we look from unit 1, what did we study? And it's such a long time ago. The things that we studied recently, we don't have to spend too much time because it should be really fresh in our mind. For example, like networking, right? The LAN, the WAN, it should already be in our mind. So I won't spend too much time on networking. I'm just going back in time to unit 1. Okay, unit 2. Well, unit 2 is graphics. I don't like the red. I'm going to change my color here. Let's do pink. Okay, graphics. Okay. Now, when we're talking about graphics, there's a couple things that we did. Compression, file size, sound, graphics / sound. And some of the things that we talked about are compression, file sizes, and we did also some, basically those are the 2 major things that we did, okay? Now, we have 2 types of image. We have bitmap, and we also have, what is the second type of image that we have that can go really big and really small. Yeah, it's a raster, is it called? Raster. Okay? So we have a vector image. It's called a vector image, but this is known as rast. Let me just double check the.
The other one.
No, the raster is the other one. So raster. I'm gonna have to double check the spelling of the raster image, but it uses math. Okay, this one uses math. In bitmap, what does it use?
Pixel.
It uses pixels. And a pixel are the small unit. It's the smallest unit of image. Okay? So these are images, and you also have to be able to calculate file size. So when we're talking about file size, you have the height and the width. How to calculate the file size? What is the equation? Can anyone tell me how to find the file size of a bitmap? Does anyone remember the equation?
Isn't it resolution
Yes, it's resolution.
times the bit
Yeah, it's
color depth,
the
bit depth. So
the color bit depth. It's a resolution times the color bit depth plus some metadata. But this small little data is not too significant. Usually they talk about it, but it's not too much. Plus metadata. Okay? If you want to remember something, this is something that you should remember. Is this equation. How to find resolution. Resolution is the number of pixels of the length. I'm going to call LX. LX stands for pixels. Time the width. Length times width is called resolution. The higher the resolution, the more pixels you have, the clearer the image. Right? You can compress the thing by decreasing the resolution, but then the image is not as clear. Then we have this other thing. It's about colors, because each pixel can be represented with an RGB color code, right? And so if I have two color, how many bits do I need to represent two colors? If I have a black and white image, how many bits do I need to represent that? What is the bit depth? Wendy? If I have black and white, how many bits do I need?
2.
I need, black and white, I can put a 0 for black, agree, and 1 for white. Agree or disagree? How many bits do I need?
What?
One little box or one little bit can hold a 0 or a 1. So how many bits do I need to represent?
1.
I only need 1 bit. Agree or disagree? Okay, so if I have 4 colors, how many bits do I need, Chet? How many bits? I need 2 bits. Agree or disagree? Because if I have 2 boxes, you can represent 0, 0, 0, 1, 1, 0, or 1, 1. Agree or disagree? You can get four different combinations, which is 4 different colors. Okay? And so you need to multiply by the bits. Do not multiply by colors. You have to do a conversion to figure out what we have here. Okay? And so 8 Uma, how many bits do we need to represent 8 colors then?
4.
It'd be 4, and then we have 16, 8, and so on. So this is the same as 2 to the power n. 2 to the power n. And so just note, do not multiply by color. So this, you must, when you're studying, remember underline bits. So that in your brain, you can think bits. If it says there's 24 colors, there's 256 colors, you need to convert that into bits. Because we're talking about file size. So just multiply this by the bits. And then metadata, who can tell me what is metadata?
It's like the date,
Yeah.
the geolocation, the resolution count,
Yeah. Color,
name.
the ISO setting, name. It's a small piece of data. They usually give you that. Okay, that depends. Some have, some don't have. The last thing you have to understand is about file size. After you've had the file size and it says, hey, we have this thing called KB. Do you remember KB? KB, MB, GB. What is bigger than giga? Terabyte. You need to understand this idea. Now, in science class, what is KB? What is KB equal to? Who can tell me what is a kilobyte? Yes. So we have the science notation. So if you're in physics class, this would be 10 to the exponent 3. Okay, it means 1,000. Each end, 1,000 bytes. Agree or disagree? Mega is 2 to the power 6. Gigabyte is 2 to the power 9, and this is 2 to the power 12. Each time, we're this timesing by 1,000. Agree or disagree? Now, in the computer class, we don't use this notation. We use the computer or base n, base 2. So, what this does, we call this KIB, MIB, GB, and TIB. This notation is what they use on the test, is they use base 2. And so 1 kilo is not quite equal, it's a little bit over 1,000. Okay? It's going to be 1024. Okay? 1024 is equal to 2 to what exponent? 2 to what exponent gives you 1024? No, 1024 is equal to 10. Agree or disagree? And so just note on the exam, they're not going to use 1,000. They're going to 1 KIB. When they say the KB is equal to 24. Okay, bits or bytes. Sorry. So if I want to do the conversion, it's just 1,000 times. So what is, to figure this one, you just go to the power 10 multiplied. Maybe is going to be 2 to the power 20. And this is going to be 2 to the power 30, and then this is 2 to the power 40. So you don't need to remember too much. You just need to remember this. If you have to convert a file size resolution to KB, Wendy, what do I need to divide this by? Because this is equal to bits. This is equal to bits. And they may say, hey, give it in kilobyte. So what am I going to do? Divide by what?
Divided by 1,000
1,000 what?
and 24.
Why must I have 1,024? You need to divide by 1,024. Why? Why can't I just divide by 1,000? It's because this is computer class, not the physics class. In physics class, they use base 10. But in computers, do computers have base 10?
I think they use base 2.
They use base 2. And so we use a kilobyte in the computer is 1024. It does not exist base 10. That's why when you do the file conversion, they're all not exactly what you think. They're a little bit more. Okay, so they use 1024. Cool? So this is the file size of image. Let's go about the sound. But you need to understand this is about data. This is about the Baoquan, about the data. KB, megabit, gigabyte, terabyte. Alright. Also, just note in here, you should note a byte is equal to what? Let's just put this. This is something you need to know. A byte is how many bits? A byte is gigabits.
8.
8.
It's 8 bits. This is something you should know. A nibble?
4 bits.
A nibble is equal to 4 bits. And a bit is just equal to a 0 or a 1. That's just 1 bit. So you need to understand about data. You need to understand bytes, nibbles, bits, kilobits, megabits, gigabits, terabits about the data. And that goes into the hardware and stuff like that. Cool. Sound. Whoop. Briefly about sound, it's the same idea where you have a sound wave, and in here we have time. And in here we have bit depth. How do we figure out the file size? The file size, you need to know the height of your max and min because we have these things called sampling rate. Agree or disagree? Do you guys remember about the sampling rate? It's measured in hertz. So this is called sample rate. Because this is an analog signal and computers only understand digital. So we have to cut it. The higher the sample rate, the clearer the sound. Okay? And then, so file size is going to be sample rate measured in hertz multiplied by the height. Again, we have the height of my data. The height of my data is called the bit depth. Times, if you have 2 sound, this is called stereo. If you have 1 sound, it's called mono. Times the channel. The channel, if you multiply by 1 if it's called mono sound, and 2 if it's stereo. Was there anything else? No. That's it. Okay? Sound is a little bit easier, but the same thing. If you wanted it to get into kV, you could divide by 1024. Okay? That would be kV. That would be kilobyte. Oh no, it wouldn't be that because you have to do the 8-bit thing. So you would have to divide by that times by 8. This right in the bottom. This would be kilo, but you would have to multiply. Let me just erase this so that you guys don't get confused. If this is going to be equal to the bits, if you want to that, it's going to be 1024 1024 times 8. Why do I have to multiply by 8 there, Chet? What does the 8 represent?
Byte.
Yes. This converts the bits to bytes. And the 1024, Uma, what does that convert to?
What is what?
1024, what is that? Why do we have to divide?
1 kilobyte.
Yeah, it gives into the kilobyte, the kilo. Kilo means 1,000. So if you want to convert sound, you multiply sampling rate by the bit depth, the height of the amplitude of the data, times the channel if it's mono stereo, and then you can do that. So in your note, you can just write down this equation, and that kind of summarizes up the idea. All right. Compression. There's 2 types of compression. I'm doing an in-depth review of the paper, okay? This is basically the same paper for May, June. Compression. Let me change the color so you know that we're on a different topic here. Compression is basically when you have data and I want to shrink it down. And there are 2 types of compressions. What are the 2 types of compressions?
Lossy and lossless.
Yes. There's lossy and lossless. Compression works for ASCII tables, for data about typing, right? Compressions work for sound. Compressions work for images. Let's talk about images. What is a lossy compression for image? What is the extension there, Wendy? What is a JPEG, PNG, GIF? Tell me a compression for a toucan.
Lossy compression.
Yeah. You lose some data. Tell me an extension.
Lose some data and
Yes.
very small size.
JPG. Okay, what is lossless there, Wendy? What is it?
PNG.
It's PNG. These are examples of whatchamacallit, images. For sound, this works also for sound, yeah? For sound, we can have MP3 and WAV, okay, I believe, are the lossless compressions. Okay, those are the bigger files. Now, how does it work? Tell me, what does lossy mean and how does it work? We need to be able to explain these. What does loss mean there, Chet? Lossy. What does loss mean? If you lose something, what does that mean?
You need to find it back.
Yes, it means that we're missing data. So how does this work? Well, I can have colors. If I remove colors, right? For example, if I decrease the bit depth of colors, okay, Wendy? If I decrease the colors, what's going to happen to my image? The file size will decrease, right? And that's one way that we can compress, is by losing data, removing color. Or if I take the resolution, and if I decrease the resolution, the number of pixels will decrease and it also saves me space. And that is the same as JPEG. JPEG removes color and therefore saves space. Okay? It's good for the internet if you want to send. You must compress because things can go easier to download on web page. What does Uma, what does lossless compression mean?
It's when the data is
Do we lose any data?
No, can you return?
Yes. No data is lost. No data is lost. Okay? This one, data is lost. How can we do that, Uma? How is this even possible? If you had to explain how does lossless compression work for a PNG, how does the mathematics work?
It's the compressed document, the decompression process reverses the algorithm.
Okay, how does do you remember in class, looking back in our notes, in class, let's say I have this is just an example, B, B, C, 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 C. This works for also language. How can I codify the same information?
And it's sort of like patterns in there.
Yeah, it looks for patterns of colors. So maybe we have different colors. This is used in the letters, but I can just use multiplication. 3 times A, 2B, and 4C. Ched, is this data smaller? Is this smaller?
No.
This has how much data there, Ched? I have 1, 2, 3, 4, 5, 6, 7, 8, 9 data. How many data is here?
6 data.
Is this smaller? Is
I
this?
think it's smaller.
Yes. And this is how it worked. Did I lose any information, Wendy?
No.
No. And so this is how it is. Lossly uses math. It uses an algorithm. Like multiplication. For same data. Okay? Write that down. A quick example is that pattern. Will this always, Uma, will this always reduce the file size? Is there any condition where this idea is very bad? Will this always work?
When there's loads.
Can you give me an example when lossless compression will actually increase the file size instead of decreasing? This, let's think about it.
Oh, like
Think about it.
like text.
So right now we have, think about the letters. We have here 9 and 6. Would there be a case where we actually get more than our original? How would that happen? Watch here. Ted and Wendy, I want eyes here. If I had A, B, C, D, E, F, G, how much data is this there, Ted?
7.
There's 7. Now, if I put this in the compression, I have 1A, 1B, 1C, 1D, 1E, 1F. What is happening to my data? What has happened to my data? Just got a whole lot bigger. It got double the size. We're going to get 14. This is an example when compression does not work for lossy. So explain why. This is the summary of this. Tell me, when is this bad? Who can explain?
When there's no data to be.
No, I want you to compare this two data. What is difference between here and here? What did I do differently? This is AAA, BB, CCCC. This is A, B, C, D, E, F, G. Tell me the difference between these two data. Yes. If there's no pattern, you're going to waste data because there's nothing to simplify. There's no algorithm. Okay? So write this in your note. This is really important. Lossy compression is not good. It's only good when there's repeatable data. Right here. When is it not good? Who can tell me in English? When is it not good?
When there's no repeat.
Yeah, when there is no repeated data. I want you to underline this there, Chet, and put this in your note. Lossy compression is not good when there is no repeated data. Alright, so that's all those file side, all from Unit 1. This is a long time ago, so I'm pretty sure we may have forgotten this. So just make sure that you get that. Right? Do you know the name of this? If you use English alphabet, it's called RLE. RLE is this method where it's a lossy compression. It's called run length encoding. Run length encoding is like run the length, how many do we have when we use the multiplication? So loss less compression. RLE, run length encoding, is used for that. Okay, done. I'm not going to do networking because we did. Logic gates. I'm going to do logic gates and CPU. What one do we need to study more? CPU? Let's do CPU. Or bit math, the math. Are you guys okay with the math? Let's go into the logic math now. Okay, math. Bit math. Logic gates / CPU. / CPU. Okay, this is the last thing. The networking, I'm not going to do because this is new and you should already have this on your brain. Okay, so we just want to review the things that we may have forgotten so long ago. Bitwise math, logic gate, CPU. So here's the quick condensed summary. So you need to, for math, you need to be add, subtract, multiply, divide. Okay? Let's put the rules. For add, 1 plus 1 is equal to what? This is binary.
Oh.
Is equal to 0 with a carry. Okay? 1 plus 0 is equal to 1. 0 plus 1 is equal to 1. 0 plus 0. This is just human brain doing this, okay? Is that? This is for addition, binary addition. This is the rules. If you can just study those rules, that's all you need. Right? We don't need to go through any problem. Okay, you do that in your notes. Subtraction, 1 minus 1. Wendy, tell me the rules.
1 minus 1 equals to 0. 1 minus 0 equals to 1. 0 minus 1 equals to 1, but with a 1 carry. 0 minus 0 equals
This is equal to 1 with a borrow.
borrow.
And this is equal to 0. This is the rules for binary subtract. Okay. Multiply. How do I do multiplication? Yeah, if I shift to the right, it means division. If I shift now, how to shift is you bloop, bloop, you put zeros, okay? If you shift to the right, it's division. If I insert zeros here and shift to the left, shift left is multiplication by how much? Chen? If I go to if I add a 0 here, and then this one is going to die, he's going to drop off, right? This is division of 2. If I add a 0, and I did the math, I don't need to do the math. This is actually really what's going to happen. It's going to be 10 by 多少? Do you remember? If I shift to the right, boop, it's 2R. If I shift to the left, it's 10 多少? Do you remember? No. It's times by 2. Okay? We can only do times by 2. Only Wendy, she's in grade 12, she can do everything. She can do the floating bit thing. It's a little bit complicated. Woo. But we'll do that next year. No problem with the math? That's the binary math. Oh, we have sign bits, signs bits, and second complement. So, this idea, I'm just going to show you the math. If I have 8 bits, this is called sign bit. And that means it's negative 128. Agree or disagree? Right? And so if you see the word sign complement, what is the very first step you do? Can computers subtract, Uma? Can computers subtract A minus B? No. We can only do addition, A plus minus B. And so computers can only add. Computers cannot subtract. So we have to do a flip bit complement. How to do it? Well, you take your bits. What is the rule for second complement? Take the bits. What do I have to do? You're going to not the bits plus 1. And that's it. That's the second complement right there. Okay, I'm not going to go into details. Sign bit. The range you can do is positive 127 to negative 128. This is the max range for sign bit. For that, all right, sign bit's done. Logic gates. Logic gates. Okay. Almost there. I know this is a lot. This is, we've been studying a lot. Logic gates, what you need to be able to do is do tables, equations, and diagrams. Okay, so let's just quickly do it. The main ones we have is and, or, not. Okay, I'm just going to do the basic ones and then XOR. The other ones are not, not and, it's just put a not gate in there. So let's put the table. Do you remember doing this there, Wendy? Do you remember doing this?
Yes.
These things you need to memorize. They don't give you this on the test. You need to know what each of these gates do for all the combinations. But after you do it, it's this is just counting in binary. Okay. Ched, AND gate. It looks like this bad guy here. Tell me, what is the output for AND gate? Yep. Can you tell me?
0.
0, 0. Very good. Keep on going.
0, 0, 1 is 0. 0, 1 is also 0. 1, 0 is 0. 1, 1 is 1.
Correct. Okay, Wendy. OR gate.
0, 1, 1, 1.
Uma. NOT gate. And then this one is, actually this is the most important because this is for adding Computers can't subtract because we only use this gate right here. It's called the exclusive OR. You do that in grade 12. Okay? Boom. The equation, these are the equations, you can use those full on, or the equations can be A and B, A or B, not A. XOR is A, exclusive OR B. That's logic gates done. How much time do we have? Is the class done? Oh, yeah. I still have time?
Just under half an hour.
Okay, good. I have time just to finish the assembly language and then that's everything. Cool? So you need to be able to draw the gate diagram. This is called truth tables. This is called truth tables, okay? And so given that, this is just the information that you need to memorize, okay? I'm not putting anything that you don't need, okay? I'm just simplifying all your notes. I'm just putting everything into the data, okay? I'm streamlining the cheat sheet, if you were to put it in other words. It's a piece of paper that you need to study. And it should just be one page front and back. That's the only information you need for paper one. If you can write really small and you can write those little things, this is only the information that you need to know. And with that information, you'll be able to get an A star on the test. Because this is what is required in your brain. The other thing is just solving the problem. Pardon me? Okay, A, yes. CPU is the last thing that we did. I'll just give you a little time to digest this. Was there anything else that we did? We did some ethics, but that was just those videos. Yep.
Not being an exam.
No. It'll be on like the real one, but it's a very small piece, so we're not going to have any programming on this test. Okay, this is for paper one. Okay, last thing. We're on to CPU. We're on to CPU. All right. CPU / the bus system. Okay. This is a big topic with assembly. Assembly is not hard because they give you the code. They give you the things. You just need to understand what are opcodes. Okay? What is a CPU? What is a bus? Okay, we're going to start with a bus. So what happens is you have CPU, and then you should know your different hardware. RAM, right? Then you have these lines. What are these lines there, Wendy? What are these lines?
Bus.
Yes. So the bus system is parallel lines and is used to communicate between the RAM because assembly language is to do with CPU and RAM. So just note that CPU, you can have multiple cores. That just means that you have more than one brain inside that. And so you can multitask. And CPU has clock speed. Clock speed is how fast the CPU can do the fetch, decode, execute. CPU can only do 3 things. Fetch data. Ooh, how come? That's interesting how it moved there. I don't know how it does that. I'm still learning. Fetch, decode, and execute. Okay? And we need to know in detail how that works. And this is all within CPU. The bus system, we have 3 lines. And this is really connecting to assembly because you need to have a digit. You need to have the address to know who you talk to. Am I talking to the keyboard, to RAM, done. And so the bus has 3 wires, if you remember. One is called the address bus. And that's like 0 times FF or something. It's who I'm talking to. And this is only one direction. Okay? You can only go one direction on the address bus. Okay, you can get you send a thing, who are you? And he says, hi, on the keyboard, my address is 0.0 times FF. And then I'm like, okay, I'm going to communicate with you. That's the purpose of the address bus. Second one is called the control bus. Control bus is like the police officer. He's the speed controller. He's the signals. It's the speed. And this goes both ways. He gives you the clock. And then the third one is the data bus. And the data bus also goes both, it's unidirectional, and that's just the road. It's the road on which the data is sent on. That's it. This is called the bus system. Okay? It's on the motherboard. And it links in perfectly to the von Neumann architecture. Because with we have this thing called assembly language. And assembly language is a low-level language, and we call this a von Neumann architecture. And who can tell me what is this, Wendy? What are 2 properties of the von Neumann architecture for the CPU?
Control unit.
Tell me what is the von Neumann architecture? Where is he?
Inside CPU.
It's inside the RAM.
Okay.
Inside your RAM, we have 2 types of data. We have data, and we have instructions. Okay? And that goes into assembly language. So we're just going to show you an example. Inside your RAM. Boop, 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 boop. This is your RAM. You have address. And then we have our data. Data is divided into 2 types. What is the 2 types of data there, Uma? Yeah, we have 2 types of data. Like, for example, MOV number 24 or LDD number 4 or something like that, right? There's 2 types of data. We can have instructions. We could also just have data in here. Agree or disagree? So you have instructions. This is what right? What do I have to do? I have data that is saved there. If I have data and instruction, he's called von Neumann. And you have to be able to do the code of the von Neumann architecture, where the address is like 1, 2, 3, 4, 5, 6. And do you remember I gave you the trace tables? But it's not too hard. What you do is do 1 step at a time. First step is you look here, you look on the table and you say, okay, move. What does move do? And you look at the table and you figure it out. There's just some moving functions, some compare function. It's all that table I give you on the test. You just have to understand what each of them do. And then LDD is, you have this thing called the accumulator. And LDD number 4 means you put number 4 here. If it doesn't have the symbol, it means you go to, if I didn't have this is direct addressing, I would go to the nigga wager, and then I would put this data into here. So that's what assembly language is like. But the key information is we have these things called the registers. We have the things called registers. And the CPU registers, I'm just going to briefly talk about them. Wendy, tell me one CPU register. And what is the very first register that we use?
MAR.
The very first thing is, after each cycle, what happens? What is the PC? We have PC, we have MAR, we have MDR, we have CIR, we have the ACC, and we have the IX. Uma, are we missing any registers? We have MAR, MDR, CIR. Is there any other special purpose registers that we have missed? ACC, IX, PC. I think we're okay. So the registers are based.
The status register.
Oh yes, there's one more. It's the flag. The status register. Okay? So, we have the very first one is PC, memory address register, memory data register, the accumulator, and we have the current instruction register. You should know what each of these do and the general idea how CPU work. Okay? So, I will go through. Wendy, what does PC stand for?
Programmer counter.
Correct. This stands for program counter. Every time through the CPU cycle, PC is equal to PC plus 1. What does this mean? Ched, what does this do? PC 加 E, what does he do? In here, after I do one instruction, what does the PC do? He go to the next instruction. 加 E means go to the next one, the next instruction. 对不对? So the first thing to know is every time you go through a cycle, the program counter increments to the next instruction. 写. Let's write this down. Program counter plus 1. What does it mean? Every cycle it points to next instruction. Does everyone understand PC counter? It just it saves the next next instruction to be do. Okay, the next address basically. The next address, sorry. The next instruction address. What does the next thing he does is from the PC counter to where this is pointing to, he's going to save that address the program counter is pointing to. I'm at number 1, I'm going to number 2. You're going to save that address in memory address register. What does a memory address register do? Saves the address that PC is pointing to. Okay? And so whatever this address is going to, it's going to 保存 into the memory address register. 对还是不对? So if I look at the code right here, okay, I'm saving this into memory address in the MAR. I'm going to save it into the MAR. The next thing is we have the memory data register. Memory data register, sometimes we just have data, which is opcode. And sometimes we have data instruction plus data. This data is put into the memory data register. Okay? It's just altering. It's like a variable, it's a fast RAM within the CPU. Memory data register, we save the opcode. Opcode is the instruction plus the operand. Wendy, what is the difference between opcode and operand?
Opcode is the command and operand is the data.
Yes. For example, LDD. And then operand is data. Uma, do we always have opcode and operand for each CPU instruction? Let's have a look at our code here. Does the memory data register always have an instruction? No, because sometimes we just have data. And sometimes we don't have any data because we have a comparator or a jump. A jump does not require any data within, so maybe we jump somewhere, and CPUs aren't smart. They just do one thing at a time. He doesn't know what data is in here. He just does the instruction. So he's not intelligent. So sometimes you can get bugs where he deletes some code or instructions instead of data. Okay? ACC. Ched, can you look in your notebook? What does ACC stand for? Do you remember the homework we did? We had a lot of ACC. What is ACC? What is the purpose of the ACC? It's about the assembly code. Do you have a calculator, Ched?
Yeah.
A calculator, when you put enter, it does the T-Swan, it does the calculation. This puts the answer to your screen. The accumulator is just to show the results of the calculation. Okay? Accumulator, it's called the accumulator, is the result of the instruction. If you're putting this into steps, actually the CIR comes before the ACC, okay? The accumulator will be at the end of the cycle because the CIR actually happens before the memory, the final answer. So technically, these are all the variable names, but technically this variable happens first. Wendy, CIR. What does CIR stand for? Have a look. This is review. Look in your notes. Look in your textbook. What is CIR? Yeah, you can look in your. Do you have your textbook? No?
Oh yeah, my book.
CIR is current instruction register, and it just saves from the MDR. We send the command into the current instruction register. Current instruction register. And what happens is from the MDR, it should look like this. The CIR, the current instruction of the MDR, and they use the double bracket or something like this, I forgot. It's basically the instructions of him he sent into to the CIR. Okay? So the notation is basically you have PC is equal to PC plus 1. Then you have memory address register. The PC pointing to goes into the MAR. Then you have the memory data register. Okay, you get the data. I forgot the notation there. And then the current instruction register gets the op code from the MDR. Put a brackets, that's the data. And then you have the accumulator gets the result. Okay, this is the notation of your transfer notation.
Square bracket MAR.
Yes, square brackets right here.
Yeah, M on the outside. And then square bracket MAR.
The MAR, yeah. I'll shift over.
M on the outside and then square bracket.
And then it's MAR. Yeah. This is getting the opcode into the data from the MAR. Okay, yes. Cool. Any questions about assembly? I gave you those little tables. There will be a table on paper 1. That's it. So this is just the knowledge part that you need to know. The practice part is if you haven't, again, this review page is on Teams, okay? Your schoolwork is, if you haven't, do a practice your schoolwork / homework is do a practice paper. Best of luck for your mock exams, okay? I think you guys will do well. There's a nice summary. If you can study the information I put on this piece of paper, it's called the fundamentals. Okay, it's like all the important information, and then you just need to, after you get that in your brain, you just need to see if you can apply it to a paper. And if you're like, oh, I know this, it means you're ready. If you're like, I'm not too sure, please find me. Ask questions. That's how we can improve. Okay?